Now, before we go on with this topic, I want to introduce the concept of phasors and how to use phasors when adding up waves. So phasors are really just numbers in the complex plane. So for example, imagine we have a wave 1 which has amplitude A1 and phase phi1. So the real part is given by A1 cos omega t minus kx plus phi1. So if we plotted the wave as a function of time and space on a graph or in animation, this is the function we would use. But we can represent it in the complex plane, where this is the real direction and this is the imaginary direction, where it has some amplitude, some stick length, A1, and some angle, phi1. And this blue stick, would be rotating around with omega t minus kx. So as you change t or you change x, in fact, this thing would rotate around. So what we've done here is we've drawn it at a moment, at an instant, where, for example, t is 0 and x is 0, so we've just got this phase phi1. But in fact, as t and x change, the angle here changes because omega t minus kx adds to the phase phi1. So when we draw these phases, we draw it at an instant, and we normally choose for convenience t equal to 0 and x equal to 0. So that's the meaning of this picture here. And then, as is normally the case when we use complex numbers to represent quantities in physics, the thing we care about in the end is just the real part. So we look at, in this case, the horizontal component along the real axis to give us the wave behavior that we're looking for in real space. Let's look at a second wave now. It has wave 2 with amplitude A2 and phase phi2. This will be the real part here. If we draw it in the complex plane at t equals 0 and x equal to 0 again, we have some angle phi2 and some amplitude A2. How do we add these two waves together? So we can take this function here, this cosine function with some amplitude A1, this cosine function with amplitude A2, and these different phases, and we can add them together, and we can stick it in Mathematica or MATLAB or Python or whatever and see what it looks like. We can also do it graphically. So if we add these two phasors together at the condition where omega t minus kx is 0, for example, if t is 0 and x is 0, this is the phasor with amplitude A1, this is phasor with amplitude A2. We take care of the angle phi1, which would be here, and this one has an angle phi2. Add them together and we get this resultant vector, this resultant phasor rather, with amplitude A3 and some new phase delta, which is this total resultant phase. So this is an example of how we can graphically add together waves using phasors. Now all these phasors, as I said, spin with this common phase of omega t minus kx, which we've ignored in these pictures by setting that equal to 0. But if we don't, then in fact we can animate these things like this. So this would be the phasors A1 and A2, and the dashed lines here I've plotted are the real parts. That would be the cosine component, like that. That's their amplitude varying as a function of time and or space. So here we could be changing t or it could be changing x. Now, if we add them together, they both rotate at the same speed, so we just pop one on top of the other, find the resultant vector, and this would be the vector A3 going like this. Mathematically, if we want to write this down in sort of functional form, we can say that this resultant function here is given by the sum of these two cosine functions, with phase phi1, phi2 giving us some resultant phase, and the amplitudes giving some resultant amplitude. But we know that the total amplitude and phase depends on both the amplitude and the phase of the individual component waves. So it's quite a complicated function. So A3 squared is given by the sum of the squares plus 2a1 a2 cos phi2 minus phi1, and the tan of delta is given by this equation here. And you can use a trigonomic construction just by adding these phasors together and using some trig to find this amplitude and this phase, and that's a little exercise that you can do. Now, a couple of important limits would be if we have equal amplitudes and the phase difference is 0, then A3 is 2 times A. So if A1 equal to A2 equal to A, then A3 is just twice the initial amplitude, and delta is equal to 0. The phase of the total wave is the same as the original. Another important limit, again with equal amplitudes, if the phase difference is pi, then the waves are completely out of phase and we get total destructive interference. So this would be constructive interference, and this is destructive interference. Of course, in the real world, when you add up waves, you probably don't just have two of them, and they can be different frequencies as well. And this method of adding up phasors is really informative for how this works. So here is a sum of waves. We're going to add up 20 cosine waves, each of them with a peak at 0 here. And when we add them up, they all have equal amplitudes. And we see that the sum becomes more and more peaked around here and starts to cancel out everywhere else. So that's what it looks like if we're adding them up and we're not having any time propagation. Now if we start adding them together and we have a wave system where now the argument here has a time function as well, then we get this sort of behavior. So we're giving it some speed here by enforcing some omega, and each of these waves has the same speed, by the way, because the ratio of k and omega is the same, and now we see these pulses moving along like this. What's this look like in terms of phasors? Well, here are the phasors for the first 4 terms, that's n equal 1 to 4, and then the red is going to be the resultant. So if we animate this, we see that red term here being the resultant of the first 4 terms, and we can see that sometimes it's very big and sometimes it's very small. But always, if we look at the real part of this phasor, that is the projection onto the horizontal axis, the real axis, then we can see how the amplitude of this wave is changing in time. In one of the previous videos, we mentioned an example of interference being the sonic boom, and now after seeing how interference works a bit more, maybe it's something we should look at again. We can see all of these point sources here. Each, as the plane flies along, it's emitting sound. Each of these point sources, if we imagine it, sends out a circular wave, each traveling at the same speed, and along some front here we get constructive interference, so all the waves add up in phase. And this photo here, you can see that the sonic boom leads to a shock wave, and the shock wave causes a rapid change in pressure as you go through it, and in this case is causing condensation at the point we have this sonic boom around this supersonic aircraft.